Dear students, we have discussed the homotopic ligands and its phases, then anisotopic ligands and its phases. The discussions we have started with a homomorphic ligands or groups or atoms, and from these homomorphic ligands, groups, atoms, we have derives three terms, that is homotopic ligands or phases, diastereotopic ligands or phases, or anisotopic ligands or phases. We have taken one example, that is such example. First example we have taken, and when you replaces Hb with deuterium and Ha with deuterium, you will obtain the if you firstly replace with deuterium, one of these isomer of hydrogen, when we replace second Ha with deuterium, these two, we obtain these two compounds, and these two compounds by replacing of Ha or Hb becomes same. These two are the same one. No steric center is there, no stereogenic center or chiral center is there. Therefore, that types of protons. These are the homomorphic protons. Homomorphic protons means what? When you isolated it becomes same and looking like same, identical and superimposable to each other. That is homomorphic protons. And all these three discussions or all these three terminology, that is homotopic protons, diastereotopic protons and anisotopic protons, is revolved around the homomorphic protons. By replacing of these, when your compound to obtain the two compound if same, then this homomorphic proton should be considered as a homotopic ligands or groups or atoms. But when you replaces these homomorphic protons, if suppose in this case we have the CH3 is there, and when you replaces your homomorphic protons, the two compounds obtained. These two compounds is obtained. Firstly we replaces Hb. These two compounds obtained are enantiomers to each other. These two compounds are when you take this compound and put on this compound, these are the non-superimposable mirror images, and non-superimposable mirror images is nothing but enantiomers. Therefore, these two compounds are enantiomers. By replacing Ha or Hb, two compounds is obtained, and if these two compounds are enantiomers, then these homomorphic protons is nothing but the anisotopic ligands or atoms. Like that way. Now, in today's lecture, we will discuss the diastereotopic ligands and groups or atoms or phases. Suppose we know that diastereomers is also observed in C double bond C compound, that is alkanes. We have such example is there. When you replace this, these two protons are the diastereotopic, which is these two protons are the homomorphic and attached to the same carbon. And when we replace Ha with deuterium, you will obtain deuterium and Hb as it is, and second compound you obtain like that you obtain the second compound. These two compounds is diastereomers. The diastereomers is also observed in C double bond C or alkene compounds. Therefore, when you replaces with these two compounds, you obtain the two diastereomers. Two different compound is obtained, and these two becomes diastereomers to each other. Okay, these two are the diastereomers. Therefore, these two protons should consider as diastereotopic protons and these two homomorphic protons becomes diastereotopic protons. Okay, well, this is the one example we have seen. Again, we have one of the example. Okay. Okay, like that example is there. Okay, that center is a stereo center. Okay, stereo center means 4 different groups is attached to that carbon. That's a stereo center. And second one is not stereo center, but it has homomorphic protons. Okay, these two are attached to the same carbon. When you isolate, it becomes same identical, and therefore that is the homomorphic protons. When such compound is there, okay, other type compound where there is a one stereo center is there and homomorphic proton is there, then it can be converted into it consider as that homomorphic proton considered as a diastereotopic groups, atoms or ligands. Okay, condition should be your molecule should have contain one chiral center and anywhere there should be homomorphic group is there. Okay, by replacing these homomorphic groups, your the two compound is obtained becomes diastereomers to each other, and these homomorphic protons considered as a diastereotopic atoms. Okay, if suppose what we said that if your compound is there, first condition your compound has a chiral center, okay, anywhere, and it has also the homomorphic groups, and if you replaces these homomorphic groups, okay, you will obtain the diastereomers. Okay, in this case we have the chiral center, okay, anywhere, okay, first carbon, second, third, fourth carbon, any carbon, if you has the chiral center is there and which is having such like that, okay, like that homomorphic protons is there, then you obtained the diastereomers, and that atoms is called as the diastereotopic atoms. Okay, in this case when you replaces Hb and Ha with deuterium, you will obtain, okay, this is your chiral center, and when you replaces deuterium is there, firstly Ha and chlorine is there, and secondly you replaces deuterium, Hb, chlorine is there, CH3, Cl and hydrogen. Okay, these two compounds, okay, the two chiral center is obtained, therefore these are the diastereomers, and by replacing of homomorphic protons, one of its isotopes, the two compound is obtained, that is the diastereomers, and therefore these homomorphic protons is called as the diastereotopic protons. Okay, now we have again some example is there. If suppose we have the example OH and H is there, and HA, He and HF is there, and when you replaces He with deuterium, okay, if you replaces with this deuterium and HF as it is, and when you replaces HF with deuterium, okay, this if you instead of deuterium you replaces the OH, okay, OH, I have taken the OH because these are the same. This compound is a trans compound and this compound is a cis compound because OH is at the same site. Okay, therefore that compound is also by placing He and HF, okay, one of this is the homomorphic protons, and it's near to its the chiral center. Okay, chiral center is there, homomorphic proton is there. Therefore, that homomorphic proton can be called as the diastereotopic groups or atoms or protons. Okay, these are the atoms. Therefore, that is the diastereotopic atoms. Okay, therefore, like that way, by replacing He or HF, the two compound is produced, and these two compounds are diastereomers to each others. Okay, but when you consider this molecule is not a chiral molecule. This molecule is not a chiral molecule. But that compound have chiral centers. Okay, these two are the chiral centers is the produced, correct? But actually, when you passes the plane, okay, that plane is passes. Okay, if you that compound you can write like that, OH and hydrogen, and then OH and hydrogen. Okay, both compounds. No, these are the optically inactive compounds. Okay, when you pass the planes, these two equal half. The molecule is divided into two equal halves, and therefore molecule is not optically active. Okay, therefore it is not a chiral molecule. It is not chiral molecule, optically inactive. Okay. Therefore, that such type of centers, after replacing of HF, your chiral center is produced. Therefore, we have seen the definition. When you replace such type of protons, chiral center is produced. Then that center is called as the prochiral center. But when you produce a new compound by replacing these two, the new compound obtained is not a chiral one. Therefore, that center is not called as the prochiral center. But when you replace it with He or HF, you obtain the chiral center. Therefore, stereogenic center is obtained. Stereogenic center is obtained, or chiral center is obtained. Okay, therefore, such types of center is called as the pro-stereogenic center, or instead of prochiral center. Okay, that is a pro-stereogenic center. Okay, instead of prochiral center, we called as the pro-stereogenic centers, and the isomers is produced is called as the pro-stereoisomerism. Okay, these two compounds are the pro-stereoisomers to each other. Okay, in such compounds, though you produces the chiral center by replacing of He or HF, that center is not called as the prochiral center, because your obtained compound is not chiral one. Therefore, that center is not considered as a prochiral center. Instead of this, there is one word, that is the pro-stereogenic center. Okay, that center is called as the pro-stereogenic center, or pro-stereo center. Pro-stereogenic center, or pro-stereo center, or pro-stereogenic center instead of prochiral center. Okay, this is one of the major important thing you have to remember regarding such types of molecules. Okay, we have discussed if the molecule has the stereo center is there and homomorphic protons is there. Okay, if suppose like that molecule is there and HA and HB, there is a two stereo center. But though it has the two stereo center, and when you replaces these two groups, it will not produce the diastereoisomers. One same compound is produced when you replace it, because when you rotate this molecule through 180 degree, okay, if you replace them, you will obtain this one and the same one. Okay, you will obtain the one and the same one. And if axis of symmetry is there, in this case CO2 axis symmetry is there, if such compounds, if there is axis of symmetry is there, and such, okay, through the axis of symmetry or through the any rotation of the axis, your these two hydrogens gets exchangeable. Okay, through the rotation, your these two groups get exchanged, but no change in this such groups is there. Therefore, like that way, if axis of symmetry, through the axis of symmetry, your homomorphic protons or the groups, if get exchanged, that homomorphic protons is considered as the homotopic. Okay, that homotopic groups or atoms, that is called as the homotopic groups or atoms. That is one of the major important things you have to remember. Okay, you have to consider the axis of symmetry is there, then that molecule or that homomorphic group should be the homotopic group. Okay, then we have another example. Okay, like that example is there. Already we have discussed OH is there, hydrogen is there, He, HF, and if HC and HD, HC and HD. Okay, these two are HCC same one, and HD is the same one. Okay, and when you passes the plane through this molecule, then this HCC is reflected one, HD is get a reflected one. Okay, or you pass the planes like that. Okay, if you pass the planes like that, this gets reflected. Okay, therefore in this case HC and HD is considered as an enantiomers. Such compound is there, like that compound. The SC and HD is the enantiomeric, enantiotopic protons. Another type of example we have COCH3. Okay, in this case also there is a stereogenic center is there or chiral center is there, and when you use that is the nucleophile, HCN nucleophile is obtained. Okay, you obtain the new stereogenic center, two stereogenic center. Okay, therefore first phase and the second phase. Okay, therefore that phases is called as the diastereotopic phases or diastereotopic front phase and the back phase. Okay, like that way that carbonyl carbon is also a diastereotopic phase. Okay, due to addition of the, okay, that one of the criteria is there. When you add after we have seen the substitution criteria we have seen, and this criteria is the addition criteria of nucleophile files. When you add to this carbonyl compound, you obtain the diastereomers. Therefore that center is the diastereotopic phases. Okay, like that way we have such example is there. Okay, other than this there is no examples is there. If you like that example will be there. I hope you will get all this idea about the diastereotopic protons. Okay, let's summarize the three phases or the ligands. Okay, we have discussed. Okay, that is first we have discussed homotopic ligands or phases, then enantiotopic ligands groups, okay, or phases, or diastereotopic ligands or phases. Okay, in such cases if you have the example like that HA and HB, when you that is homomorphic means when you isolate it from homomorphic you isolate it, and when you replace it with its deuterium, you will obtain the same compound, that is a homotopic proton. And for if the proton, for the identifying the proton, the criteria is symmetry criteria is there, and when you have the C2 or CN axis of symmetry is there. Okay, by the rotation of the, if you rotate this molecule then 180 degree like that, then HA and HB get exchange. Okay, through the rotation it gets exchange 180. Okay, in this case C2 axis of symmetry is there, and if CN axis of symmetry, after the rotation of CN axis of symmetry your groups get exchanged, then that is the you can easily say that that is the homotopic ligands. Okay, that enantiotopic ligands, if so you have the such example is there HA and HB. If you replace HA with deuterium and Hb with deuterium or He with the deuterium, you obtain two compounds, and these two compounds should be enantiomers to each other. Then for these homomorphic protons, consider as a diastereotopic protons. And symmetry criteria for this molecule is it has the plane of symmetry. If you pass the plane, so if you pass the plane through like that, these two groups, there is a exchange of these two atoms is takes place. Okay, but in this case, if you rotate the molecule with CN axis, there is no exchange of groups takes place. But when you pass the planes, it gets the exchange of this homomorphic groups takes place. Okay, therefore SN axis of symmetry are inversion. Okay, such symmetry is there. After using such symmetries, your groups get exchanged. Therefore, that groups is called as the enantiotopic ligands. And diastereotopic protons, when you replaces the homotopic, okay, in diastereotopic protons, ligands or homomorphic protons, there should be definitely stereogenic center is there. Okay, like that way we can explain the enantiotopic ligands, homotopic ligands, diastereotopic ligands and its phases. I hope you will get all these idea. Thank you very much.